Hey everyone, welcome to the last of our grade 3 standards. I kept the number and operations fractions for a week all to itself. You'll see why here in a moment. Fractions are something that many students fear. Um, and I think it goes back to the way that they were taught, that they are separate numbers from our number line. So I'm going to go over some tips with you, not only on working with fractions in the early years, but in addition to things that we should avoid as teachers so that students have the best possible chance of enjoying fractions. So fractions have a lot of different sub-standards with them. In third grade, they start at the very basic level. Some common misconceptions that we can fix before they even begin, and some of these may resonate with you. Some of you may think that 1/4 is greater than 1/3 because 4 is simply bigger than 3, looking at whole numbers. Some may think that 157 thousandths is greater than 63 hundredths because 157 is greater than 63. Or that 2/3 plus 1/2 is 3/5 because you're adding your numerators and you're adding your denominators. Or 4 plus 3/10 is 7, or 7/10 because 4 and 3 is 7. Similarly, that 4/10 and 3/10 is 7/10, which it is, so I'm not sure why I put that one there. Scratch that. 2/3 times 9 can't be 6. Heavens no, because multiplication makes a number bigger, not smaller. Or 4 divided by 1/2 can't be 8, because division is supposed to make a number smaller, not bigger. So many of you may have seen these, and maybe these are some misconceptions you have had to overcome over time. So I am going to ask you to stop rushing the algorithms. Stop rushing to the rules that I have listed here. Stop doing that. Let the rules occur naturally. Let the students figure the rules out and discover them on their own, which takes patience, which takes time, and also makes you need to have a better, deeper understanding of why and how fractions work. So here are the rules for fractions that I'm sure you've memorized along your way in education. But imagine on top of these rules how many other rules in math that we learn. So it's no wonder that students get so confused and get them mixed up together and try to combine things that they shouldn't because of all the rules that they just want. It's not about the procedure, it's about how and why we get there. So having a deeper understanding is so crucial. So some of these that you might recall are to add or subtract fractions, you might have to find a common denominator and then add or subtract the numerators. If I want to multiply fractions, I just multiply across. But to divide, I have to invert the second and multiply. And if I want to multiply or divide a decimal by 10, we move our decimal point to the right or left that many zeros. Further, you can never ever divide by 0. And to solve a proportion, we cross multiply and then divide. So many rules, and these are just fraction, proportions, and decimal rules. Let's not even talk about algebra rules and other types of things that students have to cram in their brain. So if we allow the students to develop a deeper understanding of number reasoning or number sense, students will be a lot better off within their overall reasoning if answers are correct, if they're not, and why. Rather, according to Kathleen Kramer and Stephanie Whitney, they said, set building number sense for fractions among elementary school age students as the goal, as opposed to building procedural skills with adding, subtracting, and multiplying fractions. The first standard itself says, develop understanding of fractions as numbers. We need to start treating fractions just as any other number on the number line, a single ordinary number. Stop singling out proper versus improper fractions. They're all the same. At the same time, we need to be explicit about the importance of the unit. What are we measuring? So Mrs. R drew a picture on the board. The picture I have listed there, or draw there. Then she asked her students what fraction it represents. Emily said that the picture represents 2/6. Label the picture to show how Emily's answer can be correct. Raj said the picture represents 2/3. Label the picture to show how Raj's answer can also be correct. And finally, Alejandra said the picture represents 2. Label the picture to show how Alejandra's answer can be correct as well. So we have 3 different students picking on this picture and interpreting it 3 different ways. Let's start with Emily. Emily's answer of 2/6 means that all 6 squares together make up the whole. So all of them together are the whole. And 2 copies of 1/6 have been shaded. So this might be what you see right away, the most common one. However, Raj says that there are 3 squares that make a whole. So 2 copies of 1/3 are shaded. So there's actually 2 whole pieces here. There's the 3 little squares on the left and the 3 little squares on the right. 2 of the 3 are shaded on the left, so 2/3 are shaded. And Alejandra said 2 because she says that each square individually equals 1. So I actually have 6 whole pieces here, and 2 of the whole pieces are shaded. We cannot assume what the unit is. We have to identify the unit to attend to precision when interpreting fractions. You have to be very careful about this. The earlier we start this, the better off we'll be. We also need to stop saying parts out of a whole, such as 3 parts out of 4. This limits the range of understanding when we progress through operations. Instead, use this many copies of the unit fraction. Further, complex fractions don't make sense when we say parts out of a whole. What does 3 out of 2 mean? What are 3 out of 2 things? How can you have 3 out of 2 things? Rather, we would say 3 copies of 1/2. This will then make understanding of multiplication, division, adding and subtracting that much easier for students because it works across the board. Draw, shade, or otherwise represent the fractional part of each fraction. I want to know what 1/3 of the triangle is. So we think 1 copy of 1/3. I separate my triangle into thirds, and 1 copy of 1/3 is 1 piece of it shaded. 2/5 of the pentagon. So I think of this as 2 copies of 1/5. I break my pentagon into 5 pieces, and 2 copies of 1/5 would be 1/5 and another 1/5, so 2 of them. 3/4 of my rectangle. I want to think 3 copies of 1/4. So I split my rectangle into 4 equal pieces, and 3 1/4 would be 3 of them shaded. 7/6 of, so once I cut it into 6 pieces, I need 7 copies of 1/6. But I see here I only have 1, 2, 3, 4, 5, 6. I need 7 copies. I need 1 more, which means I need to add another shape. So by adding another shape also cut into 6 pieces, I now have my 7th piece. Which number is closest to 1/2? 1/8, 3/8, 7/8, or 9/8? I see that each of our fractions have copies of the unit fraction 1/8, so I will split my whole into 8 equal pieces. Doing this, I now can label them. So 1/8 is 1 copy of 1/8. 3/8 is 3 copies of 1/8. 7/8 is 7 copies of 1/8. And 9/8 is 9 copies of 1/8, which would place me on the other side of 1. 3/8 is the closest to 1/2. Notice in the middle there that I have that 4/8 is equivalent to 1/2. Locate 1 on the number line. Label the point and be as exact as possible. Here we are only given the place value of 1/4. Well, I know that if I have 4 copies of 1/4, I will make a whole. So we will take the length from 0 to 1/4 4 times, giving me 1/4, 2/4, 3/4, and 4/4. Labeling our point 4/4 is the same as a whole. Locate 1 on the number line. Label the point, be as exact as possible. Here we have 5 copies of 1/3. So the whole is partitioned into 3 equal pieces, but we have 5 copies of them. So that means I need to split them into 5 different pieces. So I go back 5 and I label my points 1/3, 2/3, 3/3, 4/3, and 5/3. I can now label my point of 3/3 or 1 on the point. The way we have been saying fractions represents a multiplicative operator where we can expand or shrink a desired length. So if I have 2/3 of this unit, we're not quite sure how long this unit is, it doesn't say, but that's okay. I want 2/3 of this, so I want 2 copies of 1/3. So if I break it into 1/3 pieces, I need 2 1/3s. There are 2 1/3s. Notice this has shrunk our original length. I want 5/2 of this length here, meaning I want 5 copies of 1/2. So I need to split this into equal pieces of 1/2, and I want 5 copies. Well, this is only 2 copies. We need 3 more copies. With this, this would be a stretching effect. So I put the 5 copies of 1/2 there. Which is closer to 1 on the number line, 4/5 or 5/4? Let's try to explain. I'm going to use a double number line. Notice that my number line extends to the left of 0 just a tish bit, but also extends to the right of 1. We need to make sure that students know that fractions can lie either to the left of 0 or to the right of 0. All the way, it's just a number on the number line. So I see that the top row is partitioned into fourths and the bottom row is partitioned into fifths. So I'm going to label my points across the top as 1/4, 2/4, 3/4, 4/4, 5/4, and 6/4. Similarly, I'm going to label my bottom pieces using fifths. 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, and 7/5. Now I can identify where 4/5 and 5/4 are on the number line and line them up to see what we can find out. So when I line up 4/5 and 5/4, I see that 4/5 is closer to 1, more so than 5/4. We could use a verbal argument as follows. If we divide the segment from 0 to 1 into 4 equal length segments, each part would be 1/4. We can also divide that same segment from 0 to 1 into 5 equal length segments, where each length would be 1/5. The segments of 1/4 will naturally be longer than the segments of 1/5 because there are fewer of them. The distance between 4/5 and 1 is 1/5, and the distance between 5/4 and 1 is only 1/4. Therefore, 4/5 is closer to 1 than 5/4.